So now that we understand, what an alternating series is and how we can use the alternating series test to prove the convergence of a series, we're going to talk about alternating series estimation theorem. And so what this says is that if I have a series that is alternating, so in this case, the sum from n equals 1 to infinity, this is just the alternating term in there. So -1 to the n plus 1, that's what makes it alternate of some term u sub n. And as long as it passes and it satisfies the three conditions of theorem 15, which was our alternating series test, then for any index past some specified integer value, is that this sum, right, this alternating sum, approximates some value L, all right, with an error whose absolute value is less than the following term, right? So if we go up to some nth term, we're summing up to n, and we look at u sub n, the term that would follow where we cut off. So when we were adding our series, we could have said, okay, well, there's another u sub n plus 1 term here, and we're not including that. So that's the term that we're talking about. So what we can then say is that the sum, this limit, lies between any two successive partial sums. So what we know is the limit, because we're going above, below, above, below, above, below, right? We know that that limiting value that we are converging to will be somewhere between those two sums. So if we know the value of that, u sub n plus 1 term, and my value that I'm actually converging to minus the sum of those n preceding terms, that difference is going to be smaller than this u sub n term, right? So if I get to a point where I know that that value, my n plus 1 term, is small enough, I can say, well, I'm going to be close enough to my value of convergence that I can estimate what the series converges to. And we have one little addendum over here. It says whatever that difference is, it will have the same sign as the first unused term. So if the first unused term, this n plus 1 term that we didn't use, if that is negative, then this difference will be negative, and vice versa. If it was positive, the difference would be positive. So let's do an example of estimation. So here we have a geometric series, right? It's an alternating geometric series. And we're going to apply the alternating series estimation theorem. Right? So, as we generally do when we start considering series, we look at what the terms are. And so if I start listing out my terms, starting at my index n equals 0, I would get 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus 1 over 32 plus 1 over 64 minus 1 over 128 plus 1 over 256, right? And we can continue this process. We'd get a negative term next. And because this is a geometric series and we know we have a constant ratio, that ratio, for example, -1/2 divided by 1 would be equal to 1/4 divided by -1/2, or -1/8 divided by +1/4. My ratio in all of these situations, if I simplify all those fractions, is -1/2. And my first term, a sub 1, is 1. So I know the sum of my geometric series because it's going to be a sub 1 over 1 minus r. In this case, that is 1 over 1 minus -1/2. 1/3, which is 2/3. So this series converges to the value 2/3, and we know that. But I'm going to show you that if I sum, say, only the first 8 terms, what the estimation theorem says, if I sum these first 8 terms, this guy 1/256 being my 9th, the sum of the first 8 terms is going to be less than or equal to that 9th term, 1/256. So if it's less than 1/256, we're only throwing away a total portion that we're adding to the sum. We're leaving this off of our estimate, a value that's less than 1/256. 1/256 is approximately 0.0039. So 4/1,000th of a unit. So what we can do is we can use our estimation theorem. It's pretty easy for me to add up the sum of those 8 terms. And if I add up 1 minus 1/2 plus 1/4 minus 1/8, etc., all the way up to minus 1/128, the value I end up with is 0.66402625. And if I added up the sum of those 9 terms, I get 0.66796875. And both of these numbers are pretty darn close to 2/3. We knew it was going to be close to 2/3 because at a certain point, the numbers we're adding and subtracting in this alternating series are so small that they could be deemed insignificant. So if we look at this and we say, okay, well, we know that that 2/3 is going to be in between these two sums. So I've got my 0.66402625 on the left and 0.66796875. So the sum of my first 8 terms is less than 2/3, and the sum of my first 9 terms is greater than 2/3. And thinking about this on a graph, if we had, y equals 2/3 here, and we compare that to our sum, we get the sum for 1 would be above, the sum for the first 2 terms, 1/2 is below, the sum of the first 3 terms, slightly above, and they converge. They are approaching that 2/3, converging towards that 2/3 as my n indice becomes infinitely large, right? We're getting closer and closer to 2/3. So at a certain point we say, hey, we can just estimate using the first 8 terms as long as we know that it's an alternating series and it converges by the alternating series test. And if we were to take that 2/3, the limit which we converged to, and we subtract the sum of my first 8 terms, which was 0.66402625, we get an output which is 0.002604166, which goes on. And that is a positive number, which it should be positive because my 9th term would be positive, and it's less than 1/256. 1/256, I believe I get 0.39, right? So it's less than 0.0039. And that is our alternating series estimation theorem.